In this follow-up video, I want to show you exactly how I set this up and how I made these measurements of electricity waves moving down wires. And I want to do this for two reasons. First, if I made some massive mistake, I want somebody to call me out on it. And two, hopefully, if I didn't make a massive mistake, then someone else would be able to replicate this setup and use it to learn about electricity waves the same way that I did. When I started thinking about this, my biggest concern was that I couldn't take a wire and just stretch it out a really, really long distance if I wanted to be able to synchronize the scope with the beginning of the circuit and with some point in the middle of the circuit. This entire thing works because I have a single scope probe back here that keeps all these measurements synchronized. This circuit back here is plugging the battery in on and off and on and off and on and off and on and off really, really fast. And every single time that it does so, the moment that that switch flips is measured by this probe because I've plugged it in all the way at the start of the circuit. So that just sort of exists back there. And then I take a second set of probes and I will go measure points along the wire. Here I have it connected at the three-way intersection. So let's start with the switch right here. Oh wow, this is convoluted now because I just picked it up and it hung in a weird way. All right, so let's start with this circuit. We literally just start with a battery, and then we go through a voltage regulator, and then we go into this chip. This is an SN74AC14N. So that 74AC14N is a multi-Schmidt trigger. Well, it's multiple Schmidt triggers that are packaged up into a single dip there. And there was a fantastic video that I watched where somebody used one of these chips to make a TDR setup, time domain reflectometry, where you can do things like measure the length of a wire by looking at how long it takes the signal to bounce around inside of it. And this is just a really fast chip that allows you to get the most precise data. The speed of electricity doesn't change when you turn on the circuit really, really fast. But when you're trying to measure over a relatively short distance like this, the faster you turn it on, the more precise your measurement is going to be. I'm using a battery here because I want to have the most uniform power supply possible for the Schmidt trigger. I want to try to eliminate all of the noise that would have come from, like, you know, using a benchtop power supply up there where it's connected to the wall and you're going to have 60 hertz oscillations thrown in plus whatever's inside the power supply. So I'm using a battery and I'm using a couple of really big capacitors here that just smooth out the power. It gets sent through this Schmidt trigger and then, well, it gets sent through a bunch of these Schmidt triggers and then into all of these resistors. So every output from this chip is turning on at the same time. Every output gets its own resistor out here, and then I am just controlling the output resistance of the entire set. So the black wire is connected to the negative side of the battery the whole time. The red wire is what actually has the switch on it. It's a whole bunch of switches flipping in parallel, and they go out through here and they go into this pseudo twisted pair. And eventually it gets to this really fine twisted pair that I made a lot of, and this is what's actually the major runs for the circuit that I'm measuring. So we have a really fast pulse generator that should allow us to make accurate measurements. Every time this pulse generator fires, it's recorded by this scope probe that goes over here into slot 4, and that pulse gets sent down these wires into this big grid, which is what we want to measure, the big long runs of wire. I assume that most of the people watching this video about how exactly these measurements are being made also watched the video where I replicated the thought experiment from Veritasium with the parallel wires out in the big field. You may notice that these wires are very close together, and that means that we're going to have to deal with crosstalk just like we did in that experiment. Imagine that instead of this twisted pair, I was using a single wire. If I had a single wire connected to the negative side of a switch over here, when we flip that switch, we start pushing electrons into this wire, and this wire actually becomes negatively charged. That means that the electrons in the next wire are going to be repelled from the first wire, and will actually end up pushing a signal across the wires this way. What I want to measure is the propagation of a wave of electricity down a single wire. But because a single wire is going to have an influence on the wire next to it, I need to know how big that influence is. I need to be able to cancel it out. So if I have two wires, one of which I send a signal into and one of which I don't send a signal into, then I basically have a reference wire and a wire with a pulse in it everywhere. That means that when you flip your switch and you start flowing current into this wire, you create some electric field that may have an impact on like this wire. And this is actually 2 wires. So if I take the difference in voltage between these 2 wires, it should be 0. Even if both of these wires are having like some massive change to their potential, if the difference between them is still 0, then I've eliminated all of the crosstalk effects and I can only see the signal that's traveling the full distance. And when I put probes on here, you'll see that's exactly what's going on. For every one of these sample locations, I've actually stripped the wire in 2 different places. Let's see, where's one on camera? In this one, I stripped the red wire right here, and I stripped the brown wire right here next to it. So if I take my probes, and I put both of these probes on here, what I actually want to measure is the difference in potential across these 2 probes. But let's see what that actually gives us. So the green probe is the timing probe, that's the one that's attached to the switch, and then the yellow and purple probes are the ones that are attached in the middle of the circuit somewhere. And you can see that they both go up like right away. And that's because of the near-term crosstalk effects. When you start flowing current into that first wire, there's a field that reaches out and affects the other wires. And we're seeing it in both the red and brown wire. But we're seeing the exact same effect in the red wire and the brown wire, which means that we can take that difference and cancel them out. So the white trace here is actually the difference. Which way must it be going? It's going to be the yellow minus the purple wire. So in this case, you can imagine that the yellow is the actual signal that you're trying to measure propagating down the wire, and the purple is your sort of moving reference point, your dynamic reference point that you can subtract away from the yellow in order to get the white. So we can see that there's a propagation delay down. The switch flips, and then maybe 50 nanoseconds later, we see an effect on the wires where I just put those leads. So if we look at that in context here, this is the wire that's going to be affected by the signal first. And it exudes an electric field that propagates very rapidly to affect both of these wires. But it affects both of these wires in the same way. By taking the difference in potential between these wires, we isolate the signal that has gone the full length of the route. That's how I was able to get such long runs of cable in a small enough package that I could measure it with an oscilloscope on the floor. So now I can hear the question through the camera, because it's a question that I had. Which wire is the reference and which wire is the one with the signal passing through it? Do you need to have 2 switches on both wires that plug both leads of the battery in at the exact same instant to get this to work? Weirdly enough, the answer is no. There's a section that I wrote for the main video and ended up making an animation that I cut from it that I'll play for you now about why the electric signals appear to reflect when they get to the end of the wire, and I think that it speaks to this discrepancy. Why do these waves reflect? When this pulse of voltage gets to the end, it bounces back, and then it bounces back again and again. There are 2 ways that I like to think about this. First, imagine that as we're bunching up these electrons, we have to push against the electrons that are already in the wire. Since there are vaguely the same number of electrons in every centimeter of this wire, the pulse builds up to the same height hill. But when we start pushing electrons around the corner, we're pushing our wave into space that's already been depleted of electrons, since we're pulling electrons out of the red wire at the same time. That basically means that it's easier for us to push. As the wave bounces back, the electrons in the black wire get less dense and speed up. The other way to imagine this would be the case of completely isolated wires. If we weren't pushing on electrons in one wire and pulling on electrons on the other wire at the same time, then these electrons wouldn't have gotten out of the way. But still, as this wave rounds the corner, our measured signal would drop because we're only measuring the difference in voltage between these 2 points. Even if the electrons end up getting more dense at both locations, we see that the difference still drops towards 0 when the signal turns around and starts heading home. In reality, both of these are happening at once. It depends on where you put the switch and how close together the wires are, but my measurement technique very intentionally sweeps this under the rug, so we really can only actually see the simple propagating wave, because in any real situation, that's all you'd care about. You want to deliver current to a load at the end of the line from your power supply. So these are 2 different ways to think about the reflection at the end of the line, but really it gets to, are we pushing electrons into one wire and pulling them out at the same time, even though the switch is only on one wire? In all of my animations, I showed equivalent currents. I said that the coupling between the wires was perfect, so that even though we only switched one wire, the other wire had an equivalent opposite current in it. That's not totally accurate, but I do think it's the dominant effect. All the way here at the beginning of the circuit, one of the tests that I ran was to put a couple resistors on these wires so that I could measure the current flowing into the panel of cable and the current flowing out of the panel of cable. And they weren't exactly the same. In the simpler view, where you have completely disconnected cables, you would expect all of the current to be charging in through one wire, and the other wire would just be sitting there as your static reference point. But in reality, there is capacitance between those two wires. And when you start pushing current into one of those wires, current is going to want to come out of the other wire. But it's not one-to-one, which means that when you look at, how the signal reflects at the end, have we actually depleted the other wire of electrons, or is the signal just going into one wire, rounding the corner and coming back? And the answer is both. And depending very much on your setup, not in equal parts. In this case, the predominant effect was coupling between the wires, because when you've got these two twisted pair, they're like right next to each other and there's a dielectric in between them, the coupling is going to be really, really strong. But the situation that I really wanted to measure, where you had isolated wires that were like 100 meters long, then the coupling between the wires would be very, very small, and you could imagine the signal sort of literally wrapping around and coming back. So this measurement technique, where you take two probes and you measure the difference in the wires that are right next to each other, really sweeps a lot under the rug, like very intentionally canceling out other effects in order to see the propagation of a wave down a long transmission line. Now, I think the answer would be exactly the same if you didn't do this. You had a single probe and you had a single wire that was stretched out and not zigzagged, so that earlier parts of the wire couldn't influence later parts of the wire. Like, you're still going to have electrons that scrunch up in order to force current down a single isolated wire going out to infinity. But then you're not looking at the capacitance of that wire versus the other wire. You're looking at that wire's sort of overall capacitance with the ground, or, the air. It's just really hard to measure. One of the reasons that that's so hard to measure is the capacitance of that wire is really, really low. Every time that I add these probes into this circuit, in order to measure the voltage at a location, I'm changing the circuit. Now, the whole point of this experiment was to see what happens when you send electrons through a fork in the road. You've got a Y here where the current splits. But every single time that I attach these probes, I make another fork in the road. The electrons can either keep going down the wire like I want them to, or some of them divert into the meter in order to tell me how many of them are there. I got around this problem in a really kludgy way by attaching extra capacitors in front of my leads. So for all of my measurements, my probes looked like this, where I had capacitors clipped in between, and then I would use these probes to actually attach to the circuit. That meant that I only had the capacitance of these wires, which is going to be pretty small, that helped to decouple the meter from the rest of the circuit. I'm going to demonstrate that problem in just a second, but first I want to acknowledge that you never want to do this to your oscilloscope probes. If you're looking for the actual really accurate shapes of waveforms, this is going to kill it. What I've done here is make my oscilloscope probes less accurate by literally decreasing the coupling between the scope and the rest of the circuit, and by adding these capacitors that the scope is not tuned for, which means that it's probably slowing down its signal response a little bit. But I want to show you what happens when you don't use this setup. Now, the fact that I've taped these together and twisted them all together is just for my own convenience, because I needed to make hundreds of measurements. So that part really doesn't matter. Now I have two independent, focus, not on my head. So now I have two independent scope probes. My biggest fear when I started trying to make this measurement, where you're syncing it in one place and measuring it in another place, is that the addition of the probe, by adding an additional path for electricity, was going to modify the experiment, so that as you move the probe, I couldn't measure all of the probe locations at once. So when I put the probe right here, am I actually doing something to change the circuit? And the answer is yes. It's a real pain to set this up so that you, the camera, can see all of the bits that you need to at the same time. I have this yellow trace being measured from this point. So I'm measuring, some random point. It happens to be at the Y because that's where they're nice and accessible. And now I'm going to attach another probe. So if I just attach this to one of these wires right here, we see that that totally changes. The shape of that yellow waveform, the shape of what we're measuring at this point, changed because we attached another probe. So I'm going to take it away, and I'm going to put it back. That's what we don't want. We need to make sure that our measurement technique doesn't cause that to happen. If the probes are significantly impacting the measurement, when I take 60 measurements across this whole board in order to animate what happens to electricity, I'm not taking 60 measurements of the same circuit. I'm taking 60 measurements of 60 different circuits that have all been impacted different ways by having probes stuck to them. So now if I take this probe with a capacitor attached to it and I plug this into the circuit in the same location, watch the yellow trace, basically nothing happens. Okay, so holding this up to the camera a second ago made the focus go out on that and get stuck. So you couldn't see the scope at the time that you really needed to be able to see the scope. So this is the exact same setup. I have the capacitor attached through the probe to lower the capacitance of the probe. And if you watch the yellow trace over there, it's not plugged in, and now this is connected, and now it's disconnected. There's like one really tiny glitch right there. I'll do it again. Connected, disconnected, but significantly less of a change than we saw before. So this is a way to make the leads impact the circuit. I mean, you can't ever make it so that the leads will not impact the circuit. Like the moment that this gets attached, it becomes part of the circuit and there's nothing you can do about it. What you can do is make sure that this is less important than the rest of the wires. You just want to make sure that of all of the effects that govern what ends up showing up on the scope, that the circuit is, accounting for 95% of that, and the probes are accounting for very little. So now for demonstration, I've got these wires just laying here, but when I was actually taking all these measurements, I was sort of holding these in the air so that they couldn't possibly interact with these in any meaningful way. But if you want to take one of these measurements at home, what you got to do is plug these probes in, these capacitance sort of shielded probes, plug each probe into the adjacent wire so that you're measuring the voltage difference across the two pieces of this twisted pair, and then we can come back to the scope. We can see that we see the original trigger from the probe back there, and then we have the increase, in this case it's 130 nanoseconds later when the wave gets to this point in the wire, this exact location. Then what I was doing was taking a time average. So in this case, we're averaging together a whole bunch of individual measurements to come up with a really clean graph, and then you save it. In this case, we've just saved that graph as scan245.csv. You can tell that I've been doing this a lot. Once you get a CSV like this, you can bring it over into the computer and you can see that we get 3 different voltage traces for the 3 different probes, and then we get the time in seconds. You can see the time steps are exceedingly small. So in this particular case, this SDS26.csv has 3 different traces in it, and they look like this. At 0 time, you can see that this gray trace has to be the one that's connected right next to the switch because it's a very sharp increase. And the other 2 are later. So when we actually want to find our signal, we've got to subtract these out. Now, the real trick is making this not a graph of voltage versus time, but making it a graph of voltage animated in time. So for that, I wrote a script that brings in one of these slices. Didn't break. Where is it? There we go. Wait for it. There we go. So while individual graphs may look like this, when you actually animate it, you can see a single point in the circuit and you can see the voltage rising and lowering over time. Then the next trick is to make lots of these measurements. So these are the sheets that I was keeping track of this on. Every time that this oscilloscope happens to save a CSV, it pastes a number on the end. So I was spatially plotting where each trace came from. In this case, like this would be the Y-shaped circuit right here. Actually, and then looks like I crossed that out, and then I went this way. So you got all these numbers in the first wire, all these numbers in the next wire, all these numbers in the next wire, and this was the fork in the middle. And I basically wrote a script that would allow me to plot these spatially. So I can go in here and I say, I want plot 6 to be at this point, I want trace 8 to be here, 10 to be here, 11 to be here, 12 to be here, and then it'll go and it'll turn every one of these into an animated bar chart. There we go. After much importing of data, that looks like this, which you've already seen in the other video, just with like more annotations on it. Of course, this also records the entire trace, so we're sitting here waiting for 900 nanoseconds of animation to pass by. But every single point on this graph, every one of these bars that's moving up and down is a separate measurement that was made, actually an average of many measurements that was made at a specific point along that circuit. And their position here on this graph, their XY position, is representative of how those wires were actually connected, of course, omitting the zigzags. And there we go. And it's just that easy. And the final question that I wanted to address about this setup is, why did I bother to twist my own wire? You can go buy a twisted pair. I could have used coax, but I decided to make that custom twisted pair because I wanted the wire to be more resistive. Having nothing to do with the impedance of the wire, I wanted the actual resistance to be high, so that when I was looking at this graph, there would be a notable decrease in voltage here. The rest of the circuit has resistors in it. Like, there's resistance built into the power supply. There's resistance, well, in some of my tests, there was resistance at the load. The resistance of the wires needed to be significant enough that when all was said and done, I could see that decline, because I wanted this graph. I wanted it to look just like the image from the electricity maze video, where you've got the descending gradient and you've got the plateaus. Like, there's always going to be a voltage drop across a wire unless it's a superconductor. But in practice, the files that are saved out of this oscilloscope are not a very high bit depth, which means that if I want to be able to measure the peak of the wave in the same measurement as seeing this slow grade in voltage once all is said and done, I needed to artificially increase the resistance of the wire, which required winding my own twisted pair. So I hope that you found that interesting. If you want to try to repeat this experiment, I hope that this was enough. If not, ask questions in the comments. I hope that I didn't make any mistakes, but I think that the data and the visualizations I got out of this were really cool. I really enjoyed this project. So with that, I'll see you next time. Thanks for watching.